Today another hard problem, hopefully not for 2 hours. Longest increasing path in a matrix. We got longest increasing path. You may not move diagonally or move outside the boundary. 200 by 200, so we can do n cubed in quotation marks. That is interesting. I think the strategy for this clearly is to just start and longest increasing path. Well, I would start from 1, and from that I can go here or here in 1, right? And then add this to Q. But this 200 is very suspicious. It will be 2000. But knowing Leetcode, it could also be linear, so maybe it's like 200 times 200 times logarithm, which it probably is since it's sorting. So I said, okay, I can get here in 1, I can get here in 1. And then first I would put everything in a queue, right? And now I would take the first one and I update the longest paths here, and we will never go to already visited. Since we can only increase, so we will never go back. And if I have 1 here and then 1 3 1 2 3, right, then I will get here, I will choose 1 and I will not choose 3 until I get there from another one, and at that point I will have the longest path there. So let's do this dijkstra. So first let's grab the sizes of the matrix. Here I assume that matrix has at least 1 row, which is true. So first I have the value in there, and then I have the, maybe I should have a vector, so, or let's do a struct. So first I have the value in that position, but then I have to do a custom sorter on the entry. And I don't remember how to do that, so let's do vector of ints, which will be our priority queue. And now we just insert each position, and that longest path we can get there is length 0. So pq insert, and now we insert the value there, so matrix ij, then we insert length of the path. I think that doesn't matter because we will always have just 1 instance of that. And finally we have the position. Longest path to here. That's fair. But maybe I should store these so that I can properly index this. So longest paths all have length 1, and this will have length 1, and now while not pq empty, then what we do, well, we grab the top right, that is pq, let's call it like element pq begin, and let's dereference it, and then we take pq erase element, who cares. Okay, so int value element 0, then this current list is element 1, and then ci l2 and cj. Okay, and then we go through delta dx. So what I'm doing is we have to iterate over the neighbors, and instead of having some sort of a like array of the deltas of x and y, I just have two arrays for delta of row and delta of column. So I can calculate the new row by previous row plus change in row at that index, and then new column is old column plus delta of column. Now, if we are inside of the grid, and it's a larger position, it is worth trying going there. Let's do new list. Let's do this. I mean that sounds really unnecessary if we have weights 1. And distance of new I new j is smaller than distance of ci cj plus 1, so we can get there by a longer path. Here is what we want to do. First of all, we update the distance. That's just current distance. Okay, and then we have to do, before that, pq erase matrix this, length of the path is this, and then we erase it, and then we insert it again back. What we do is we have to erase the old entry and insert a new one. So we erase the old, update distance, and insert the new one, and I think that is it. This one, let's do 0, and no return statement. Okay, and there is some error. Okay, still error. Okay, too soon. Let's see, looks like an infinite cycle to me, but okay. Time limit exceeded. Ah, I know why. And the value in that cell is larger. And matrix ni and j is over matrix of the current position. Now it should work. Great. Let's submit. Easy business. Oh my days, I did something very slow. Looks like. Editorial, let's see, editorial, knife, that's TLE. Peeling onion. I mean, I guess it's a dog, that's true. So I'm just doing a dijkstra on a dog. Who cares? Whatever. Okay, you can do a dog. No one cares. No one asked. Okay. No one asked. Actually, I could really speed this up because that is inefficient. Yeah, okay, let's speed this up. This is a bad solution. So dijkstra was approach 1. I would still do sorting, right? Okay. Then we have okay, and then well, what I'm doing is trying to do the recursion, so I go for its position. Okay, now if this ij, so it wasn't here, then we run DFS from here. Finally grab the answer. So first we check our cache. Right. Otherwise, we go through the neighbors. So if all this holds and matrix new I new j is smaller than matrix ij, right, then we have current is max current and 1 plus DFS and INJ. This ij is current. This should also work, I think. I cannot call auto. and then I should pass self here. No, type self. Voids int, boom. Oh, this should return int. Okay, that works too. It should be faster. Okay, that's better. Maybe I can save some time in here. Let's do this, and then I can skip this entire thing. Let's see how that does. 12 milliseconds. Meh. Why am I getting a clock, bruh? Whatever. Okay, let's write a solution now. So dynamic programming. The longest path ending in each cell, i.e. dp ij. The longest path in. Think of the simplest backtracking solution. Start longest path in ij is longest path is maximum of longest paths of neighbors which have strictly smaller values is 1 plus this is a simple backtracking. Can you think of a way how to speed it up? Just use memoization, i.e. when we have already computed the longest path for some cell, we do not have to compute it again. O and M, where N is the number of rows, number of calls, since we visit each cell O1 times during the DP table computation, and for each of them we do O1 of work. O and M, since we store longest path ending in each cell. Great. Okay, this was much more pleasant than yesterday. Goodbye.